Okay. Yeah, so great. And actually, since I created the YouTube channel, I noticed that people are using it. So I'm really happy. Like Manga Cat, he's in Taiwan, he cannot join us. He was very happy to be able to see your talk. So it's a great thing. So Antonio, please go with the Rita's Desk Super Geometry Seminar Part 3. Go.
Okay, very good. Okay, so let me first recap a little bit what actually we have discussed last times, and so let me give you a kind of a very simple overview. So we have three types of objects that we discussed. We have this. We have the superforms, and I will denote the superforms by these symbols: omega, p/0. Okay, so 0 means 0 pictures. So in the pictures, okay, so in the language that I presented the last times, 0 pictures means no Dirac delta functions, and p is the form number. And as we have seen, the form number p could be any number greater or equal to 0, and the picture is 0 in this case. Okay, so the superform are the usual forms written in the basis of d-axis and d theta. I'm still keeping as a basis of my space Rn/m. So this is my super space, like the reference superspace, which is just a local description of my supermanifold. I'm always working on local patch in this talk. Okay, I will not talk about the global issues anyway. So these are the superforms. Then we have integral forms. And integral forms, I will denote them by this symbol p/m. Okay, so m here is exactly the m here, which is the maximum number of the thetas of the fermionic direction of my superspace. So in this case, the picture is m. So this is the number of the picture. And the p is again a form number. But in this case, the form number p could be less or equal to m, but p could be also negative. Okay, so p could be any number from -infinity to m. To n. Sorry, gosh. Okay, so to n. Okay, that is the maximum number of form, which is equal to the dimension, the bosonic dimension of my supermanifold, but the p could be negative. We have seen how it could be negative because, okay, those objects are those written locally in terms of the product of all delta functions, okay? And therefore, actually, I can act with the derivative of delta function. And a derivative of delta functions plays the role as a negative form, okay? So this form could be have 4 numbers which are negative. Finally, there are also another space which are called pseudoforms. In this case, I denote by p/q, and the q is the picture number, and p is the form number. And in this case, the form number p could be any integer from -infinity to +infinity. Okay, so I can add the power of d thetas, I can take derivative with respect to d theta, and so therefore I have no upper bound, no lower bound in this particular space. So a nice way to represent those spaces is the following. Okay, let me write down, draw a complex, a big complex. So in the first line, I have this object, omega 0.
Antonio, I have a question. So when you talk about the picture number, right, which is in the integral form is the number of odd dimension, right?
Yes.
So is this number equal exactly as the delta appearing?
Yes.
Not the delta, is exactly that, right?
Is the number of deltas with or without derivatives. I mean, the derivatives doesn't change the pictures, okay? It's just the number of deltas.
No, the number of delta without the derivative.
No,
right?
no. The number of deltas without or with the derivative. It doesn't matter if you have a derivative. It just counts the number of deltas. Because the derivative doesn't change the picture. The derivative changes the form number, okay? The picture is just the number of deltas.
Then we can do some example of integral form where you integrate where you have some derivative just to understand. Because I don't understand the derivative thing. I understand the, when you say m is the picture number, this is fine. And p is less or equal to n, that's fine. But this presence of the derivative is a bit confusing.
Well, I don't understand. I mean, sorry. So let me make an example. Okay, for example, you want to make an example. Okay, so this means an omega, for example, an omega, let's say 0 m, for example. Okay, this example, okay, this is an integral form. Okay, one local form could be like just the delta function of d theta 1 times of delta d theta m. Okay, this is certainly an example, and this is a picture m. Okay, because you have all the possible delta functions. There is no derivative, and the form number in this case is 0.
Yes.
However, for example, you can also have this one, for example, dx1, let's say along the direction 1, and then I have a delta function of d theta 1 times the delta function of d theta m. But then you see this dx is in front increases the form number, and so then I can put a derivative anywhere. For example, the first derivative of the first delta functions. Okay, so this means a derivative of delta function with respect to its argument. Okay, and this plays a role as a -1 form. Okay, so then the total form number is a +1 in these cases, -1 in these cases, give you 0 again. Okay, so in this way, for example, another one.
We have delta theta 2, delta d theta 2.
Yeah, of course. The next, okay, if I write down the next factor here, okay, let me write the next factor. The next factor will be something like delta of d theta 2, delta of d theta 3, and so on up to delta of d theta n. Of course, you can also have this one, dx1, delta of d theta 1, delta prime of d theta 2, for example, and also the others. Okay, it doesn't matter where you put the derivatives. Okay, you need one derivative. Okay, in order to decrease the form number. The picture is always the same. Okay.
Okay, thank you.
Okay, now let me make a nice drawing. Okay, which is the following. Okay, let's make it this drawing. So I have 0, forms. Okay, 0, forms. Then I have 1, 0 form. Then here I have omega 2, 0 forms, and so on. Okay. Now, of course, this is a complex. So let me write down, as usual, in the complex in this way. Okay, where these arrows here on the top of the arrows, I put the differential d. So the differential d actually moves from one complex to the other, so from one space to another space, just by increasing the form number. Okay, it doesn't touch the picture number, but increases the form numbers. Okay. Then let me write down the integral forms. Integral forms means what? Omega 0m, for example. Then I have omega 1m, and so on. Sorry, let me first do it this way. For example, omega 2m, and so on. I can have omega up to n/m here. And then, okay, again, here I have a map. Again, the differential d. Then this because
Antonio, am I the only one with the?
No, we can't hear you.
because
No. I can neither.
okay, and therefore
We have problems listening, Antonio.
Repeat. Antonio now is gone.
Can you hear me now?
Yes. Now we don't hear you anymore.
Now, can you hear me now?
Yes.
Okay, can I go on?
You have to repeat some things because we lost like a couple of minutes.
Oh, okay, very good. Okay, so okay, first I described the first line. Okay, the
Yes.
first line is the superform line. Okay, so this is a complex. Okay, where I wrote down all these spaces: omega 0, 0, omega 1, 0, omega 2, 0. So all these spaces belongs to the superforms complex. Okay, and the differential D moves from one space to the other by increasing the form number. Then the last line I wrote down here, this is just the integral form line, okay? The integral form line, where actually, again, the differential D moves from one space to the other one. And then I would say, okay, look at this space here, the omega n slash m, this represents the top form, and therefore the last step, when I computed the last step, the differential of the top form, then automatically I get 0, okay? However, I have to remember that also I have a negative for number, so I can go negative here, okay? In this case, I go negative here, and also I can go negative on these directions, okay? So therefore, the first line, it extends from above. The last line, it extends from below, okay? But then here in the between, for example, I can have like omega 0q, and then I have omega 1q, omega 2q, and so on, okay? And this extends to this side, but also it extends also on the other side, okay? So I will have also here the omega minus 1q, and so on, okay? Again, the errors between those spaces are obtained by acting with the D differentials, okay? So differential D, actually it acts in a horizontal way. So it maps the spaces, the complex, without moving among those complexes, but it just moves horizontally in the space. Okay. Let me make just one remark about the differential D here in this line. Okay, Simone in his talks was talking about the Koszul differential. Actually, in a more rigorous and, let's say, in more mathematical language, indeed it is not just the differential, it's just the Koszul differential in the space, okay, which has to be defined correctly. And he did it in these slides, in his talk, in his papers, correctly define the Koszul differential. However, from a handyman like me, okay, this differential, when it is represented in terms of integral forms, as I did, it coincides with the usual differential. So I will use the Cartan calculus as always. So for me, the differential D, it is defined in this way, because actually I have an explicit realization of those spaces, and therefore on those specific representation, the Koszul differential introduced by Simone indeed coincides with the usual differential. Okay, let me give you an example how this works. Suppose that I consider a form like omega, this one, omega 0m, as I did before, which is just a function of x and thetas, and then I have dx1, okay, delta prime of d theta 1, okay, and then all the other d thetas, okay? So now this object is what? Is an integral form with the 0 form number, because you see there is a dx here and one derivative here, and then all the possible delta function here, all the possible m delta function. Let me show you how the differential D works in this case, okay? Let's do a very simple calculation. Let's calculate what is the D on omega 0m. If you do these calculations, of course, okay, I have to remember that acting with the one forms like dx1 gives you 0, acting on d theta 1 or d theta m gives you 0. So the only part that I have to compute is just a differential acting on the function in front. So differential in the function will be something like dx with some index, let's say I, with the derivative with respect to I of the function f. And then I will have something like d theta alpha with, now here, this is a super derivative, okay? Let me write down explicitly, okay? of f, and then I have a dx's 1, and then all the deltas here. Okay, now let me rewrite this expression. You see, this expression will have a terms which is a proportion to dx1 or dxi. Okay, and of course these terms it gives you two results. Either the I is along the x1 and then it gives you 0 because dx1 wedge dx1 gives you 0, or otherwise you get the dx2, for example, wedge dx1 with the derivative 2 of f. And then I have the delta function, delta prime of d theta 1 times delta of d theta m. Okay, so here indeed I increased the fourth number. What happened? Okay, of course, if I have a derivative along dx1, that's give automatically 0. What happened to the second term? Okay, you have two situations. Either the d theta alpha is in the same direction as the derivative here.
The picture is greater than 1 in that case, right? Is 1. So the so when you do d omega, you get something that is in 1 because it has increased the 1.
Yes, yes, of course. Of course, this object will be something omega 1/m. Yes.
Okay.
Okay. And in fact, it does coincide because you see here there are two form numbers from dx2 and ds1, and then here there is a derivative. So totally gives you +2 from here, -1, and total form number will be +1. Okay. Let's see what happened to the next term. I could have two situations. I have a d theta 1 derivative with respect to theta 1 of f. Then I have a dx1 delta prime of d theta 1, and then I have all the other thetas here, d theta m. Okay, this is the first term. However, I can also have like something like a dx2 derivative with respect to d theta 2 of f. I have a dx1 delta prime of d theta 1, then I have d theta 2 and times delta d theta m. Okay, and of course I also have all the other terms. Okay, now the two situations are different. You see, in this case, these coordinates here, it is exactly the coordinates appear in the derivative of delta. Then for that, I use the following equation: d theta 1 delta prime of d theta 1, that is equal to minus of delta of d theta 1. Okay, so this is a distributional equations, okay, which tells me that I can do integration by parts. This is just integration by parts, as I did last time, integration by parts, which allows me to exchange the derivative on the delta function with just the minus. On the other delta function with the derivative, for example, it just hits the delta function with the d theta 2. And therefore, in this case, I use the notation that the d theta 2 delta of d theta 2, that gives automatically 0. And this, again, a distributional properties. So this line here drops out, all the other lines drops out. And the final result of this calculation, now it is just dx2 wedge dx1, derivative of f, time of delta prime of d theta 1 times delta of d theta m, and of course also all the other terms. But then for the second line here, I get a minus derivative of d theta 1 of f, and then I have a dx1 delta of d theta 1, delta of d theta 2, and times all the other deltas here. All the other terms, all the rest drops out from the calculation. So again, you see here the four number, it is respective because this has a four numbers +1, and here there are no more. There are no more delta functions, no derivatives on this delta function, and so the total form number it is +1. Okay, so I show you that the differential d acts on integral forms as usual, and it maps the integral form of the case Pm into integral forms of the case P +1/m. Okay, so it exactly increase the form number. Now, so as I said, in this particular representation, since I have an explicit representation, this differential, which correctly Simone points out that is the Koszul differential, in this particular case, coincide exactly with the usual differential on my supermanifold. I can apply my calculation as I did for superforms. The same trick, exactly the same tricks also works in the case of pseudoforms. Namely, it also works in this particular sector. Also in this particular sector, the differential D does exactly is a dirty job and indeed increase the form number as usual in this case. Okay. So then, of course, what you can do once you have a differential D, it is of course is a coboundary operator, and it has all the good properties that we know and love about the differential D. So, and therefore we can calculate cohomologies. Okay. We can calculate cohomology. And therefore we can define the cohomologies of differential D of spaces P/Q. Okay, so that's actually we can calculate all the possible cohomology we can calculate, and this is just the RAM cohomology of these spaces. Okay, so therefore we'll have the RAM cohomology for superforms when actually we have this one, the RAM cohomology of superforms P/0. Okay, then we have the RAM cohomology of integral forms omega P/M, and finally, of course, we have the RAM cohomology of pseudoforms when P and Q are now. And so therefore we can define the RAM cohomology on all possible spaces. Okay. Now, of course, please.
Antonio, these cohomologies, given that in this case we are considering Rm/n/m.
Yes.
I expect these are all trivial, so to say.
Well, this is almost true. Okay, this is almost true because now I want to show you one non-trivial cohomology. Okay, which is the following one. Let's consider this one, omega 0m. Okay. Now this space is an integral form of 0 form degree and picture number m. Okay. And first, let me write down the representative, okay, of this cohomology, okay, and then we'll discuss actually what is this object, okay. Let me write down in this way, okay. I have take the delta of theta 1, theta 1, and then I have delta of d theta 1, okay, times all the same along the same structures, okay. So I just write down this object here. So it's a theta 1 delta of d theta 1. Let me show you first that this is indeed an element of cohomology. Let's pick up one term. Actually, in the literature, those are called Y0/1. Okay. So you see, I put all the possible deltas, and in front of them, I put all the thetas. Okay, in this way. Let me show you first that this is indeed the cohomology. If I act with the differential, I have a theta 1 delta of d theta 1 in this way. Then if I calculate this object, I get d theta 1 delta of d theta 1. Then if I act with the differentials, so I have to go through of the thetas. So I get a minus sign theta 1, and I have delta of d theta 1. Now this one gives you 0 because the delta of d theta is 0, because delta of delta d of delta d theta 1 is equal to delta prime of d theta 1 of d theta 1, and this automatically gives you 0. But you see there is also these terms here, okay? There is also these terms here, but then I use again the usual distributional property that gives you 0, okay? So therefore, this is an element, so this is, of course, is closed. First observation. Then I have to show you that it is...
I don't understand what there is, I'm confused. So d theta prime, d theta prime. Why there is a minus?
No, sorry. It is not theta prime. It is theta 1.
Sorry, theta 1. I meant theta 1. So you have a d theta 1, the delta d theta 1, and then why a minus there? I am confused.
It is this term is a minus because if I go through with the differential and I hop over the theta 1. So as I said in the beginning, in the very first lecture, I said I use the following setup. Whatever is commutes with everything, whatever it is, anti-commuting with the anti-commuting objects. So D for me is an anti-derivations, okay? So it is an anti-commuting operator, and theta 1, it is again an anti-commuting variables. Of course, you can do it also in the other way, okay? So you say, well, D is an anti-commuting operator, and theta 1 is an anti-commuting variables. You can keep the difference between the two. You can do also that one. Okay. Unless, if you are consistent with your notation, then you don't get mistakes. However, I prefer to use this double parity assignment in such a way that differential D for me is an anti-derivations and the theta is an anti-commuting variable. So therefore, if I have to exchange, so if I go through the differential and it goes over the d theta 1, then I get the minus sign. Okay?
Yeah, okay.
Good. Now, actually, I still have to answer Paolo questions, and then I have to show you. Okay, I show you that is closed, but I also want to show you that is not exact. And how can I do it? Well, the way to do it, okay, so the simplest way to do it, it is, of course, if I integrate this object, then I should get 1, okay? So let me integrate this object here. Let me integrate this object here, and then let's suppose now that I'm in very simple situation. I have just 0, 1. So it is a space which has a no bosonic direction and just one fermionic direction. So my cotangent space, okay, of this one, R0, 1, it is now described by two coordinates, theta 1 and the d theta 1, okay? And then to be precise, I will have the parity inverted cotangent bundle in this way, okay? So then my integral, okay, so now I want to do the integral. I want to integral of theta 1 of delta of d theta 1, okay? Let me write down here the coordinates on which I integrate. Okay, so I just listed the coordinates. So I will have to do the integration on thetas, and I will have to integrate on the thetas. Okay.
No, but Antonio, you lost me with the parity change. So theta
no, very simple. No, Rita, it's very simple. Theta 1, it is an anti-commuting variable. D theta 1 is a commuting variable. That's it.
Why do you need to reverse? I am confused. Why do you reverse the parity?
Well, let's say in mathematics, okay, you know that the cotangent bundle, it is just a bundle, okay, of bosonic coordinates, okay? So you have just two coordinates, okay? Now, actually, what I'm considering the coordinate as really the differential, the thetas, okay? So then you change the parity because of this, okay? That is the reason why, okay?
No, you lost me with the parity because so the way you're saying it, if you take the cotangent bundle, theta is odd and d theta is even, right? Right. Now you change the parity, you want theta even and the theta odd. I am confused.
No. Theta is always anti-commuting. Theta is always odd. Okay. But usually when you consider the cotangent bundle, okay, let's consider a bosonic manifold. So I have x coordinate and you have the p coordinates. Okay. But both are commuting coordinates. Okay. When you take the parity changed cotangent bundle, you have an x coordinate, but then you consider dx coordinates, okay?
Yes, but the thing that disturbs me is that you seem to take the parity change for the cotangent on R, the way you're saying it.
But I mean, this is R01, okay? So R01 is a super manifold which has one fermionic coordinates, okay? So if you do the parity change of this, I get the usual coordinates for thetas, and for d thetas, I get the commuting ones. Otherwise, you get the same type.
Okay, so your coordinate is d theta 1.
Yes.
And I see. So you take d theta as your coordinate, okay.
Yes, but actually, this is the things that we have done from the beginning. The d theta are my coordinates in the cotangent bundle, okay?
Okay.
Okay. So then if I have to do this integral, okay, the first integral here, this is just the Berezin integral. Berezin integral means I get here I get just 1 because it's a theta 1, d theta 1. Just the Berezin integral of one coordinate is just 1. And then here I have the integral of delta functions. Okay, by integral of delta function, everything gives 1. Okay. which is the usual integral. So therefore, to answer Paolo's question, indeed, this simple object in 0, 1, okay, is a θ1 of delta of d θ1. This is an element of the cohomology H of omega 0, 1, okay. This object here, it is known in the literature as the picture changing operator. I will show you why this is so, okay, what is the meaning of this object here. And indeed is an element of the cohomology, okay. Well, actually, this object were discovered, okay, they were introduced in the literature years ago by people doing topological strings. Then lately in 2014 by Nathan Berkowitz in pure spino string theory, and then together with Roberto Diego Matessi and Marco De Bernardi, actually we show that indeed the RAM cohomology, besides the RAM cohomology that you know, Paolo, there is only this object in addition. Okay.
So it seems like you integrated over this shifted cotangent bundle.
That's right. That's correct. Yes.
But why? But I thought that Y, this Y01, was a section of the Berezinian on R01, and so you should integrate it over R01, not the shifted cotangent bundle. Why the difference?
Well, actually, I'm integrated in the parity shifted one. Yeah. Not in the usual cotangent bundle, but in the parity shifted one. Yes.
Because
otherwise I would have to integrate it doubly with the two Berezinian integral. Yeah. But actually, this object θ1, the delta of d θ1, this actually is transformed as a Berezinian object. Okay. It is not. I mean, if you take it θ1 and then if you don't change the parity, and therefore you don't take the delta function, this object will not transform as a Berezinian. Yeah.
So does it or does it not transform as the Berezinian?
This one I wrote down here, it transforms exactly as the Berezinian. Yes.
Right.
And so then here I'm integrating really a section of the Berezinian. Right.
So I would say that what stays in between is an integral along the fibers, because basically the symbol in the brackets does not actually transform, because if you look at that space, that parity shift tangent bundle as a super manifold, that is well, let's say a Calabi-Yau. So the Berezinian is actually trivial. So that guy in particular does not transform, and the isomorphism is realized somehow in this way as a sort of integral along the fibers. So you first integrate over the dv θ1 and then over the other part, and that other part is an ordinary Berezin integral, I would say, something like this.
Yeah. Yeah.
I don't know.
No, John, if I understand something, these brackets, they're only to remind us where we are integrating. They don't contribute. Am I right? They don't contribute.
No. Wait.
No. Wait a minute.
This is truly a section of something. In particular, that measure is a section of the Berezinian over the full tangent bundle, yes, seen as a super manifold. But in particular, that symbol is quite nice because it turns out that that's super manifold as a canonical measure, because that super manifold is a super Calabi-Yau.
No, I'm not questioning how nice it is, the point of view, but I'm saying, suppose you eliminate the bracket, you get the same result.
Absolutely. In fact, I disagree with Simone, okay? In some sense, this object is completely useless, okay? Totally useless, because it is not an explicit representation of this object.
Antonio.
Which object is this object?
The bracket, the square bracket, these guys here. This guy
Antonio,
here.
And Simone, are you referring to like the analog of Liouville measure on this odd symplectic manifold? Is that?
Yeah, pretty much. I mean, from my point of view, that symbol over there is just the Berezinian, like a section of the Berezinian for pi t of, well, in this case, R0/1.
Well,
so
yes, it is not dangerous, this term, because it is invariant.
Exactly.
It is a section of the Berezinian
it's totally
of the
useless.
tangent bundle.
It's totally useless. It doesn't.
Yes,
I don't want to
maybe,
spark.
maybe.
No, actually, Roberto, we have discussed it thousands of times. This object is always to remind.
But I still need to integrate over superspace, so I still need a section of the Berezinian.
I wrote down the integral. Yes, I wrote the integral. That's the integral is enough to do everything what you would want. Yes.
So my point of view is that I have a section of a Berezinian, and I need a particular class of function that actually take care about the integral along the fiber, which is a bit of a problem because the fiber goes like R, well, in this case R, and R is non-compact, so I need something that actually, you know, regulate the integral. And this is something is actually the deltas.
Right, exactly. So yeah, exactly.
So is this thing in brackets what you were calling the fake Berezinian? It's like I remember during Simone's talk you mentioned some fake Berezinian.
Okay, so the fake Berezinian is
or is that
well, let's say like a joke, and is what I have called the Berezinian in my talk, I would say.
But that's is that okay? Is it Deligne's construction of the Berezinian where you take like the X group of something?
Yeah, exactly. It's basically that cohomology class that involves some dx and some derivative with respect to some thetas.
Yes, but it is not this object. Okay, this is just only half of them, half of the integral. Yeah. It is not the integral of the whole spaces or the cotangent bundle, of course. It's just the integral of the.
So that particular hex, so that's computed by Deligne or Manin, is truly the Berezinian of the supermanifold, and not the Berezinian of the full parity shift tangent space. So this instead is the Berezinian of the full parity shift tangent space. And I mean, you can quite easily see that this Berezinian is actually trivial, does not transform, because basically you can see that this space, well, the space of forms on this space sits into a short exact sequence of a certain kind. And if you take the Berezinian of the short exact sequence, you have that the injective and surjective part are actually the dual one of the other. So all in all, you have something which is trivial. So this is how I see.
Okay. So let me give you now another interpretation of this object here. Okay. Now let me let's consider the following. Suppose that I have a submanifold. Okay, suppose that I have a submanifold R1, okay, just a line, okay, and then I want to actually emerge this submanifold into a supermanifold, R11, okay. Suppose that I want to do it in this way, okay, and I will do it in the following, okay. The way to embed this object, I will do it just, okay, so my space here is just parameterized by the following coordinate, x1, theta 1, okay. And then, of course, if I consider also the cotangent bundle, so I also consider the coordinates on my cotangent bundle, I have dx1 of d theta 1, okay? So therefore, actually, the way to embed R1 into R11 is just to say, well, let me put the theta 1 is equal to 0, and the d theta 1 is equal to 0. So this is a very simple way to emerge the R1 line into my supermanifold R1/1. Okay, so the immersion here actually can be constructed using a Poincare dual of this immersion. Okay, so the Poincare dual of this immersion, indeed, it corresponds to this object 1, 0. And the reason is the following, because actually, if I want to realize this particular setup, I can do the following. I have delta of theta 1 of delta of d theta 1. Of course, when actually I integrated on my coordinates and then I put a delta function along these coordinates, means that the delta function set the coordinate is equal to 0. So in the case actually for just the fermionic coordinates, so the first terms did actually it coincide with the fermionic coordinates. And so this object here is indeed, this is the Poincare dual, okay, of the immersion of R1 into my supermanifold R11, okay? So the way to see that this is an element of the cohomology is this is just a Poincare dual, okay?
But,
so there are...
Antonio, you lost me with the equality. I don't understand that equality. What is it? Why is it so? I don't get it.
This one?
Yes.
Well, the delta function of one fermionic coordinates, it does coincide with the coordinates itself.
Okay. Because yeah, I didn't look. So it is not d theta, it's delta of theta prime.
Right. So this is the reason why I get these coordinates. Okay. So then, okay. So to answer to Paolo, actually, this class of cohomology, it represents.
Sorry. Can I have a question?
Yes.
If you change, if you scale thetas, you would expect that on the left you get one of some constant, while on the right you get exactly the constant because of the transformation rules of the
yeah. So if you scale the thetas, for example, suppose that you scale the theta by constant c, okay?
Yeah, exactly.
So then you get that the d theta 1 is also scaled like a d theta 1, okay? However, when actually you consider the scaling of this, okay, it happens the following. The object in front is scaled like this, but then you have a delta of the scale of this one, okay? However, the properties of scaling of delta function, it is exactly the inverse. So you get 1 over c of delta of d theta 1, okay? And therefore, this one cancel with that one, okay? So indeed, it is a scaling variant, yeah.
Yeah, okay, I completely agree with this, but yeah, my point is that when you replace the theta with theta, I mean,
this one, this equation here.
Yeah, if you replace theta by c theta, now it's kind of no problem. I mean, no problem arises. But if you want to parameterize something which is not like the submanifold theta equal to 0, but for instance, some linear combination of thetas, and you do such stuff, I mean, take out the theta, maybe you get some problems.
No, it doesn't create any problem. It always works correctly. Yes, right.
Yes, but I'm confused about that delta theta prime equal theta prime, because in my very vague understanding of the delta, don't you want like to, I remember we were evaluating when the argument was 0. I'm confused. At some point, the delta had some function says, oh, you know, it is delta, that has to be 0. So yeah. I'm confused a bit on this. Why
you are confused about distributions of these types? I don't understand.
No, Antonio, don't give me you are confused about distribution, because these are nothing but they're not distributions. They are something else. So don't give me you are confused about.
No, Rita. No,
I am. Yes.
When you integrate and you have a theta.
Yes.
It's the same thing as integrating with the delta, because when you integrate with theta, what is it? It extracts only the 0 degree.
Yes.
And the delta of theta means I extract only the constant part. So the two operations coincide.
Right, exactly. I agree, yeah.
Okay, I will think about that. Okay.
It's like you have a Fourier series, a Fourier expansion, and you take the constants only.
That's right, exactly. That is exactly what the delta function does. If you look in the Fourier transform, it's just the zero term. Yes. It's called also the mass of the function. Yes.
Mm.
Right.
Yeah, I understand what you're saying. I don't see it here, but it's okay. I will think. I mean, what you're saying is totally fine with me. I understand the mass, the constant is that I don't see, but it's okay. Let's keep going.
Okay, very good. Okay.
So, Antonio, there was my question. You have answered my question. Thank you. I have a small question, but you don't need to answer it. I just want to formulate it. Then you can go on. It looks like all this cohomology that you're showing us is a kind of interesting representation of some more abstract cohomology that should be taught as simply algebraic with no deltas, d's.
Yes.
That should have to do with some Lie algebra or
Exactly.
Chevalier-Eilenberg cohomology. Should be something like that, no?
Yeah, okay, you're perfectly right. Indeed, this is a work that we have been doing with Roberto, Carlo, and Simone. Actually, we did indeed compute the algebraic object. And together with Carlo, for example, we showed that using Hochschild-Serre cohomology sequence, spectral sequences, that indeed you find this object from a more algebraic, abstract way. Yeah, you're right, completely, yeah. I would be happy to show you. I mean, we have a beautiful result which is purely algebraically without using any deltas, indeed. Yeah.
Okay.
Yeah, yeah. Indeed, actually, it is exactly last year we started with Roberto, Simone, and Carlo to analyze the Chevalier-Eilenberg cohomology, where indeed you have the full algebraic powerfulness, and there you can do it without using even representation. Okay, it is actually this delta representation is very useful to do the calculations, but indeed should be defined in a very algebraic formal way. That's I completely agree. Yeah. Okay, so let me show you other two nice interesting things. So if you consider this object here, as I said, this is an element of cohomology, okay, d of theta 1. Of course, I could have also the other one. For example, I can have another one along the other coordinates, delta of d theta 2, okay, and then I put all together. So y 0, 1, wedge epsilon 0, 1, okay, all together up to get something which I will denote by 0/m, okay, which is just the product alpha goes to 1 to m of delta alpha of delta of d theta alpha. Okay, that is the object. Of course, this object has a picture m, okay, but then it is something nice that I can do is the following. Suppose that I have a superform P0 with these types, okay, and then what I can do is the following. I can multiply this object by 0m, wedge, just only multiplication, just wedge multiplication, P0. And then you see this object, it is automatically an integral form, okay? So when I multiply these two objects, I get an integral form. So indeed, this object here, it is known in the literature as the picture changing operators, okay? Because this object here, the finally operator, okay, it changed the pictures. So going back to our drawing, okay, going back to this, okay, it happens that the picture change operator, it acts vertically. Now it moves vertically among those spaces, okay? So it really produces from superforms, it produces pseudoforms, it produces integral forms, okay? So therefore, it is an object which maps vertically. That's the first things. The second thing, it is an object which is which is closed. D of y 0m is equal to 0. And so therefore, not only map the spaces, but also maps cohomology. If I have a cohomology of this type, okay, by the picture change operator 0m, it maps into the cohomology, okay, P/m, okay? So it maps cohomology into cohomology because y, it is closed, it is not exact, and indeed it maps cohomology into cohomology. So it is not only a map between spaces, but it's also a map on the cohomology. This is quite interesting because now, if you look back in our drawing, okay, let me show you again the drawing. Suppose that I have here omega 0, 0. And then here we know that the first step is 0. And then I move to omega 1, 0, and so on. Okay. But then let's look at the last line. It is omega 0, m. Okay. And then I have omega 1, m, and so on. Okay. But here I get something which is omega minus 1, m in this way. However, here, of course, there is no cohomology because this is completely empty. And therefore, if I map these spaces in this space 0m, it turns out that also the cohomology of these spaces, which is minus 1m, is completely trivial. So there is no cohomology here. Okay? So then I learned something that's interesting. The full cohomology of my spaces will be contained in just a box here. Everything which is outside of the box has no cohomology by definition. This is just a very nice result that the existence of this picture change operator allows us to say, well, look, there are no cohomology outside of this box, okay? And the full cohomology is always contained in just a finite dimensional boxes around this complex of forms, okay? This is one thing. The second thing is that once I have this picture change operator 1, 0, which is just a theta 1 of delta t theta 1, then you can ask yourself, okay, look, but this is just a representative, okay? So it is a representative cohomology class. So therefore, I can change this object by exact terms without changing the class. I just change the representative. And of course, by changing the representative, I can do several things. First of all, I can write down this object in a way that it's nicer. For example, nicer means, for example, it respects some isometries, for example, and then you can do it. Or, for example, you can write down this object in a way that is more suitable for your calculations. Okay, that's the first thing. So then you can ask yourself, well, but this is related again to some embeddings, okay? So again, this manipulation here, it respects to a manipulation. We know the dual actually are related to the homologies, okay? So every time you have an embedding, you have an homology class which tells you how you embed this object in the big manifold. And therefore, you have a dependence on the homology class. So the representative of the homology class, it is represented as represented as cohomology classes in the Poincare dual, okay? So therefore, if I change the embedding, suppose that I change the embedding, let me write down a variation of the embedding of the picture change operator. Suppose that I change the embedding. It is very simple to prove that the change of the embedding, it is exact. Let me write down exact like here. Okay, so the change of the embedding, it is always exact. So therefore, I know that my my picture change operator, it does depends only on the class. It doesn't depend on the representative. So all these features are very important because the reason is that when actually you do calculation in string theory, these picture change operators are crucial, okay? But then you like to insert in the calculation something which doesn't depend on the way you write down this object. It depends only on the class. And indeed, these objects are those elements, okay? So that actually, it gives you a way to construct by this map, okay, this is a beautiful way to construct integral forms starting from superform, okay? So there is a nice map between them. Let me get to the last part, okay? Let me get to the last part, because actually, if I can move down, okay, if I can move down here by using the picture change operator, then one nice question is, why cannot move up, okay? So suppose, is there an operator which moves up, okay? Namely, an operator which removes delta functions. And then here get to the very nice point here, okay? So how can I remove some delta functions, okay? Suppose that I have a delta function of d theta 1. I want to remove it, okay, from my form. Well, the way to do it is actually I have to invent another differential operator which does that, okay? Of course, if I act with differential here, it gives me some differential of this, get some derivative. So acting with differential d, I get the derivative of delta functions. So it doesn't change the pictures. It doesn't change the delta function. And in addition, actually, I have a contraction operator along a vector, along a not vector, for example. And of course, this is equivalent to take a derivative. I mean, a contraction along a vector, it means removing some d thetas, but it doesn't change the picture. However, the contraction operator along a not vector, okay? Suppose that I have a not vector. Let me write down this odd vector explicitly, this one, okay? So this is a not vector field, okay? Of course, it's anti-commuting. So if I get d squared, this is equal to 0. So it's an anti-commuting vector field, okay? Then I take the contraction operator along this vector field, d theta 1, okay? Then it turns out that this operator here, if I take the square of this is not 0. So a contraction operator along a not vector, it is not a nilpotent operator. So we know that in the case of even vectors, a contraction operator along an even vector is a node operator, okay? An anti-derivation, okay? If the vector fields is not vector fields, then automatically the contraction operator along that vector field is now an even operator. Okay? Good. Of course, if I act with this
Antonio, isn't this a trivial consequence of the fact that d thetas are even, right? That is why.
D theta. Well,
you can stack them.
Yeah, you can. Actually, it is exactly what I'm saying here. If you do a contraction along d theta 1, so this is even, this also must be even, and then it gives you 1. The contraction along the vector fields, which is the dual of the one form, give you 1. It gives you 1, but indeed, since this one is even, then automatically also this one should be even. Okay, but here comes the nice things. Okay. So if I have a differential operator with an even differential operator, then I can write in something terrific, which is just the delta function of these differential operators, okay? Delta function of this differential operator is indeed a kind of a differential operator, okay? And then it turns out that if I calculated this object, this gives you, again, 1. Okay, let me do more precisely. Let me put an I here. Okay, Roberto will like it. Okay, if I put an I here, everything turns out quite nicely without any I around. Okay, let me show this equation here. Let me show how this works. Okay, there are different ways to see it. Okay, let's say the best way, the well-sounded way, it is using conformal theory, but I'm not going to do it now. Now, for a Dirac delta function, I have an integral representation of them, okay? So let me use the integral representation. The integral representation means integrating between minus infinity to plus infinities, dt. This is just a kind of a dummy variables, e to the minus to I of my operator, which is I of contraction along d theta 1, okay? This is my operator here. Now here, so let me do the small calculation. I get the minus sign at dt e to the minus, sorry, there is a t here, okay? T of the contraction along these vector fields, okay? Now this operator will appear here. This is just what? Well, this is just a translation operator along the thetas, okay? So this is just the Lie derivative along, it is just the exponential map along these vector fields. Therefore, if I act with this operator, I of d theta 1, and then I act on the delta function, this gives me, well, it's just a minus, so it is the integral of dt e to the minus t of the contraction operator along d theta, acting on delta function on d theta 1. Okay, now I have to finish the calculation. You see, this operator, it degenerates, I write down here, it generates translation along d theta 1, okay? So this means what? Well, this is just the integral of minus infinity plus infinity of dt, and then I have delta function of d theta 1 minus t, okay? It is translated along that direction. Then finally, I can do the integral, but because this is an integral of delta function, and then finally get 1, okay? So it's very nice. This equation, I think this was invented by Schwarz, Alex Schwarz, these equations in one of a very fast first paper, and then was elaborated by Belopolsky some years ago, and then actually we use it. Okay, together with Carlo, for example, we published a long paper where actually we describe indeed how to do calculation with this object. Okay, it's tricky. I mean, sometimes you have to be very careful because okay, you are dealing with some conventional integral and you are dealing with delta functions which are not really delta distributions. So you have to be careful. Sometimes you have to regularize the integral before taking the correct integral. Anyway, so we have a nice paper with Carl where we describe all possible situations and how to deal with them. Okay, certainly it would be very interesting to have a more formal derivation of this. Okay, let me get to the last point. Okay, so now we have this operator here, which is a delta function of a contraction operator along the vector fields. Okay, this is not the whole story. Of course, I can do something even more dramatic. I can also write down a heaviside delta functions of this operator. Sorry, I'm getting very bizarre object. Okay, but then for that I use again a integral representation, which is just a minus infinity plus infinity e to the I it of the contraction operator. Sorry, this is the contraction operator. So it is I of d theta 1, and then the delta function is defined in this way. Well, you have to take the limit when epsilon goes to 0. That is just the integral representation of heaviside theta functions. Heaviside theta function means just the step function. It's just a step function. Gosh, it's just a step function 0 here and then 1 from here from on. Okay, this is just a step function. This is just a theta function of x. Okay, now actually I can write an operator which is a z, okay, which is defined in this way. It's just the commutator of differential t d with a heaviside theta function, theta 1. Okay, and this is just my operator here. Okay, let me explain this formula, which is certainly, it is a rather complicated expressions. Okay, this formula tells us the following. Okay, look, this object here seems, okay, first of all, it is closed because it is a commutator with the differential d, so it is a closed operator. Okay, however, it is not exact because the heaviside theta function, it is not a compact support distribution. So with the heaviside theta function, we're getting outside of the space, which are just only low.
I don't understand this integral. Denominator is t plus I what?
Well, actually, this you have to read in the Schwarz book how this is defined a heaviside theta function. Okay, so I'm not reviewing distributional theory. Okay, heaviside theta function or.
But you may explain the letters on the board. What is epsilon? I don't get it. What is it?
The epsilon.
No, I see a symbol. I don't understand. What is the is the
epsilon? This epsilon here.
Yeah.
Well, the epsilon.
Antonio, you forget the limit for for epsilon
okay.
going to
there is
0.
A limit. Okay.
Yeah. But there is a limit, Antonio.
I'm sorry. This obvious. Okay. Well, it's
yes.
The limit. Okay. Of course, I'm taking the limit. Okay, that's all.
But Antonio, be patient with me. I want to know the names of the things that.
If you know complex analysis, of course you know what does it mean. Okay, you know, for example, what is the principal value? Okay, it is just the limit of epsilon go to 0 when the two integral coincides. Again, this is epsilon go to 0. Of course, this is just the epsilon term as usual. Anyway, I mean. I don't have to explain the epsilons. I mean, there's everybody knows.
It's the usual epsilon notation.
Yeah, okay. Right. I mean, just take any.
Okay, that's fine. I mean, that's fine.
Good. Sorry. So therefore, this object here, okay, this is a z operator, okay. This z operator, what does it? You see, this object here, okay. If you calculate what it does the following. So let me do the calculations on some object. Suppose that I act on delta function d theta 1. Now, this operator here, if you just use again this integral representation, it gives you a nice answer. It gives you just the inverse of d theta 1. Of course, I mean, here we are really somehow on the wedge of something which is very badly defined. The inverse of d theta 1 is certainly defined. Okay. However, those actually we study with the Simone and Roberto. Those are called inverse form, and actually in the literature that actually appear in string theory much before than actually we use them. It is called in string theory. It's called a large Hilbert space. Large Hilbert space. It is a Hilbert space of some string theory Hilbert space which contains some inverse of these delta functions. Okay. And however, it turns out that even though we are going a little bit in this very strange and weird space, the final answer d of something, okay, then automatically put you back in your nice space made of d thetas and delta of d thetas. So actually, this operator z is called a picture lowering operator. It maps from Pm to omega p m minus 1. So it changes indeed the pictures. So it removes one delta functions. It doesn't change the form number. Okay, it doesn't change the form number, and indeed you're happy. Of course, this operator here also preserves cohomology, so maps cohomology into cohomology, and so therefore you can use them also to do nice calculation. Let me do the last remark. Actually, if you calculate, for example, what happened, for example, z acting on y01, okay? Let me do the calculations, okay? The calculation, it works in this way, okay? I have d of theta along derivative of d theta 1 acting on theta 1 of delta of d theta 1. Let me do this nice example here, okay? Let's see what happened, okay? So let me write down all the steps. Okay, so I have d acting on theta of I contraction along d theta 1 delta of d theta 1. That's the first term. The second term, it is just yeah, I put a plus because this is an anti-commutator, not a really commutator. But anyway, I have a theta, and then I have I of delta. So this is the contraction along the vector field. And then I have a d acting on delta 1 of delta d theta 1. Okay. Now we know that it is an element of cohomology. So this object is automatically 0. So I'm left the first line. The first line, let's see how this works. This operator here, okay, this operator here acts only on the direct delta functions, and it doesn't touch any the theta appear here. Okay, so let me go through. Okay, so this means I move then, so I get the d. Oh, sorry, I wrote in red. Okay, so I have d, and I get the theta 1. So I get the minus sign because I go through this object here. So now I finally have theta of I of delta of d theta. So the contraction. Yes, the contraction d of d theta 1, and then I have delta of d theta 1. Okay. Then I use what I was discussing before. I use this equation. This equation gives me d of minus theta 1 over d of d theta 1. Then finally, let's do the last calculation and get the minus d theta 1 over d theta 1. Okay. And so then finally, this cancels with this. I get the minus 1. Okay. So indeed, this picture change operator z, actually, it is a kind of a formal inverse of the picture change operator y. So if one raises the number of delta functions, the other one lowers the number of delta functions. So they are somehow kind of inverse one each other. Actually, this equation, it is also well known in string theory, where actually you place with the picture change operator exactly in the same way. So I think that somehow this is the starting point of this nice geometry. Okay, so we have all these differential operators, and out of them you can build. The last things I want to tell you is that there is one additional operation that you can do, well, there are, of course, there are other differential operators, but there is one additional operation, which is the Hodge dual operator. Hodge dual operator star, okay? The Hodge dual operator, okay, it maps pseudoforms into Hodge dual of them. So this means, sorry, it means n minus p, m minus q operator forms, okay? That's Hodge dual operator. We work out with Roberto and Leonardo Castellani. Is an involution operator, which is just equal to plus or minus 1. Okay, it's an involution operator. It is well defined. It maps, okay, for example, it maps superforms, P0. It maps into integral forms, for example, and back, of course, because it's an involution operator. It maps pseudoforms in pseudoforms. And of course, the Hodge dual operator requires a metric, okay? Then you have to define a non-degenerate metric on your supermanifold. If you have such an object, then automatically you can construct Hodge dual expressions, of course. So plain, okay, this operator here, this Hodge dual operator was not present in the literature before we did with Roberto and Leonardo. And indeed, it's very useful to build some action, you build some operators using just differential geometry as a, and this Z operator and this Y operator plays roles in different applications. Together with Carlo, Roberto, Simone, Leonardo, we work out several examples and several applications of those operators. I think that everything I want to say is here. So I have a big space of object PQ, okay? I have some differential operators Y and Z, okay? The differential operator D, I have the Hodge dual operator. Of course, I will need also the metric on these spaces, okay? And then you can play with this geometry, okay? First of all, we have not played, for example, with other structure like gerbs in this game. But I think that all this calculation that has been done in bosonic framework can be reproduced in this super manifold framework, okay? And of course, it will be very interesting to see actually how, if there's something different, what we know in the conventional geometry, okay? I think that nobody really explore this part of the geometry, of the super geometry in this sense, okay? So I think that I will stop here. I think that I've spoken so much now, okay? That's fine. And
very, very good. So are there questions? The audience has been very active, so now it is time.
There's one question that I've been kind of holding, which is if you have one of these, if you have one of these integral forms with a derivative on the delta, and you integrate that, how does the derivative affect your calculation? I mean, what happens?
Yes, okay. Suppose I have an expression like some forms here, okay, which certainly depends on x's, dx's, thetas, and d thetas, okay? And then here I put some other forms and integral forms with derivatives. Suppose I have something like dx's and then some derivative of d thetas here, okay? Okay. So when I do this calculation, this derivative delta function will act on d theta by integration by parts, essentially. Of course, if I don't have any d theta here, by integration by parts gives you 0, okay? It gives you no contribution. However, this derivative delta function plays a very nice role, okay, in some calculation. As I show you, the picture change operator y, it is just theta of delta of d theta. Of course, you can add here something like dx, okay, and then delta prime of d theta. For example, you can add easily these terms, okay, and then you can ask me, okay, well, what these terms? Why you needed these terms, okay? Well, actually, these terms play a crucial role, for example, in superspace technologies, okay? For example, because these terms here allows you to have supersymmetry manifest, okay? Because otherwise the supersymmetry, for example, this object here, this part here, the picture change operator, it is not manifestly supersymmetric, okay? Let me tell you more precisely, okay? What is a supersymmetry in this language? Supersymmetry in this language is just a translation of these coordinates along, let's not confuse it with this symbol. Let me write down symbol like just length epsilon. This length epsilon, it is just an infinitesimal fermionic translation of the data. And the supersymmetry transformation of X is something like theta epsilon, okay? So this is the supersymmetry. Of course, a nonlinear realization of supersymmetry in these coordinates. Now, if you immediately see, if I make a supersymmetry transformation, so let me put an epsilon here to remind us, this is just a supersymmetry transformation. Supersymmetry transformation of this, it is just epsilon delta of d theta. Now, d epsilon is 0 because this is a constant parameter. So then you see, this is, of course, it's different from 0. However, this object you can write as a d exact, okay? So this means that the supersymmetry of the picture change operator, it is not manifest. It is a supersymmetric in the sense that it belongs to the same cohomology classes. However, if I want to write down something which is supersymmetric, okay, I can do the following. Let me introduce this v, which is dx plus theta.
I think we're losing your audio again.
Oh, really? Okay.
Audio and video also.
Okay, now it seems
It seems better now.
Yes,
yeah.
yes, it is better now.
Okay, so probably I'm too fast and the connection doesn't keep me.
That's right.
So then, okay, so this V, okay, this V is now is a supersymmetric. In the literature, this is called supersymmetric line element. Okay, okay. So then, what I can do, I can write down the picture change operator Y. Okay, in this way is the V delta prime of d theta. Okay, so now this object is manifestly supersymmetric. So then, to answer your question, John. Okay, now how this works? Well, okay, suppose that I want to integrate some Lagrangian, and my Lagrangian depends on V, it depends on this size, and okay, and then I multiply by this picture change operator Y, then you see that this derivative acting on delta functions actually plays the role as a integration by parts, and therefore it extracts the part along the size. It turns out that if you do the calculation in this way, namely using manifestly supersymmetric picture change operator, the answer, it is automatically a superspace integral, okay? Namely an integral which is usually a superspace integral of superfields, which is automatically supersymmetric, okay? So the use of this delta prime derivative delta function allows you to have manifestly supersymmetry. And the way to do it is, of course, by integration part. Of course, if there is nothing on which this acts, that automatically gives you 0. Okay. So, for example, in the paper with Roberto, with Carlo, and also with Leonardo, so we have several examples where actually we show that by changing the representation of the picture change operator, it doesn't change the theory, okay, but it changes the representation of the theory. Either you have a component theory in component, either you have a superspace integrals, and all are related by just changing the representative of the picture change operator. This is not always true. There are, of course, there are some caveats in this argument, but in general, this is true. Now, actually, we show with Leonardo, Roberto, and other friends, we show that indeed all the superspace formulations, okay, all the superspace formulations are related by changing the Poincare dual. Okay, just changing the representative of the Poincare dual, it connects all the possible superspace realization, namely component realization, superspace realization, harmonic superspace, pure spinor superspace, any you mention it, you have it. It's just a change of representation of the Poincare dual of the immersion. It's very beautiful. I mean, it's a kind of mother theory which interpolate between all the possible representation of a superspace. Do you want to have an equal to superspace? Well, you have n equal to superspace, but you can also have n equal to superspace in n equal 1 superfields. You can have n equal to superspace using harmonic superspace, or you can have half a superspace. All this realization is just achieved by changing the representative of the Poincare dual of the immersion.
Okay, so more questions?
I actually have 2 questions. this fact can be, this very fact you have been considering right now, can be used to somehow, instead of speak of supersymmetry in a given frame, component formalism or superspace, can be used to simply say, well, there is a bigger supersymmetry and formulate theories in this bigger space with a bigger symmetry group, let's say.
Yes, let me answer that. This is a very nice question. The picture change operator, actually, they were invented by Martinet, Frieden, and Schenker in string theory to do exactly that. You start from worksheet superstrings. They have super diffeomorphisms, okay? So super diffeomorphisms are gauge symmetry, okay? And therefore, you gauge fix this supersymmetry, and the gauge fixing of the supersymmetry, it gives exactly the picture change operator.
I lost you.
So can you hear me now?
Yes.
Okay. So this means, okay, let me repeat.
No, it was perfectly fine. You arrived at the full stop.
Okay, very good. Okay. So now you can do the following. You can try to understand if indeed there is a bigger symmetry, bigger gauge symmetry, whose gauge fixing produce exactly this picture change operator. So your question is very good because it should be there, okay? And indeed, actually, you can view the Faddeev-Popov gauge fixing, the Faddeev-Popov trick, indeed as a picture change operator, okay? So the answer is yes, it should be a formalism where you obtain the picture change operator by gauging a bigger symmetry. Indeed, yeah, you're right.
Okay.
But actually, nobody did it in this framework. It would be very nice to do it in this geometrical framework. The gauge symmetry there.
The gauge symmetry there, yes.
And then by gauge.
I lost you again.
Fixing that symmetry. Okay.
Now it's going fine. Let me remove the video.
Uh-huh. So,
not yet.
Gauge symmetry, which should produce.
No, Antonio, it seems it's not working.
So it's gone.
Now it's working.
Okay, it will be very nice.
Antonio, can you hear? We cannot hear you.
I don't know what to do. Actually, what can I do is I can switch. Off the
È sparito.
Niente, si vede che adesso spengo la registrazione